and share the results of our poll, which you can see that most people responded that oxygen, carbon, and iron atoms were created in the insides of stars. So we have a few people saying Big Bang or in interstellar space. And Tim, I'll leave it to you to answer this question as you go along. So why don't you, oh, actually, I have more introducing to do. Sorry about that.
Yeah.
Yeah, all right. So I'm going to stop that poll. As you all know, those of you who may have just joined us for the very first webinar, you need to advance this.
Yes,
slide.
I will.
Thank you. I'm Mary Dussault from the Smithsonian Astrophysical Observatory, part of the Universe of Learning team here at SAO with Erica Wright, who's also on camera. Today's overall presentation is going to be led by Tim Rue at Space Telescope Science Institute. And along with him is Brandon Lawton, our outreach scientist from Space Telescope. Advance a slide and you'll see our Smithsonian Affiliations team that all of you affiliates know very well. And Patty is on the line representing the Universe of Learning project at Affiliations. And then I want to give a special welcome to Dr. Lou Strolger, who's going to be our guest speaker, a subject matter expert later on in the webinar. And he's, I think, going to tell us a bit about dark energy, that strange, mysterious phenomenon that we've mentioned in a few prior webinars and that everybody has questions about. So thanks for joining us, Lou, and I'll introduce you again later when we start. Today's webinar, if you'll advance a slide, Tim, is going to go over our dynamic universe. How did we get here? A little bit about galaxy development, a little bit about star life cycles from birth to Earth. Then we'll have Dr. Strolger start talking about dark energy and go over some resources. So without further ado, Tim, the floor is yours.
All right. So first I want to touch on that poll question that Mary put up earlier. Where do those elements form? And only about 25% of the high school students who answered that question got that one right. And there are those results again. Thank you, Mary. And the correct answer here, as most of you guys chose, is in the interior of stars. We'll talk a little bit later in the webinar about how stars change, how they're born, how they die. But there's a big misconception out there that the universe was born in the Big Bang just as it is now, with galaxies, stars, and all the various things that we see up there. But as we'll see today, the universe is continually changing. So then, oops, there we go. Trying to clear the poll off of my screen as well. The night sky. Some people have, I was just saying, some people have thought that, with maybe the exception of the moon, it always looks the same up there. However, I mean, we can just look out in the sky from month to month and see how, or even over the course of a night, and see how the constellations change and the stars move. There's this, if you take a still picture of the sky up there, you can see star trails due to the rotation of the Earth. So there are things changing. That's not mentioning comets or meteors, but there's even more change than that. You might recognize this from an earlier webinar. Over the course of billions of years, galaxies have been moving, colliding, developing. We saw what baby galaxies looked like about 2 weeks ago, and you can see those there on the left, and looking a little bit reddish as the light has stretched out a bit over the time of the universe's life, and those baby galaxies are also a little bit irregular, and as they get older, the spirals are getting a little bit more defined. You can see. Let me move my pointer here so you guys can see. You can see as you move to the right, they're getting a little more defined. Until they develop into the sorts of spiral shapes that we know today. But those galaxies are moving in relation to each other, and it's possible for them to collide. Right here, you can see a couple different pictures of the antenna galaxies. On the left, you've got a Spitzer picture. On the right, you've got a Chandra picture. In the middle, you've got one of the Hubble pictures you may have seen around before. And those are all of the same galaxies that are colliding together. And I'm going to pull up a little visualization here. And, oops, oh no, there we go. Play. So this is a visualization of how a collision could proceed and how that leads to the shapes that we see in the sky. And I'm also going to take advantage of the internet. Play this at about double speed. So you can see a juxtaposition between pictures of galaxies in the sky and how those might form as different galaxies collide with each other. The gravity of each galaxy is pulling things out of shape, but when galaxies collide, you're not seeing stars colliding with each other. There's so much space between those stars that they're actually passing right by each other. The gas might compress and create new stars as it's going along, but most of the stuff that we recognize as matter, the baryonic matter you might have heard before, is not actually colliding. Oops. See if I can get that to advance. So there are a few of those pictures that you saw over the course of that visualization, a mosaic of a bunch of different galaxy collisions. Lots of different galaxies are showing evidence of collision. And you might remember last webinar, we also saw some evidence of dark matter as a result of a galaxy collision. And this is not just limited to other galaxies. Our own galaxy is going to be colliding with the Andromeda galaxy in the future. Not to worry, we have a couple billion years before we get to that. In fact, the sun might be around the end of its lifespan by the time that happens. But there is a visualization based on predictions for this, which you can access on Hubble site, or you can look at ViewSpace, which we've talked before, to see some of that. And yeah, Mary is pointing out the difference between visualizations and real data observations. These right here are pictures that we've taken of the night sky, stuff that's actually out there. Visualizations are those computer models based on the science that we've learned and the data that we've gathered, but they're not actual observations. We cannot see galaxies colliding because it takes time. It takes so long for that to happen. So there are a couple different types of galaxies that are recognized up there. There are spiral galaxies, as you see on the left, irregular galaxies, which are they're just not regular shapes, as you see in the middle, and they come in all sorts of different types. And there are elliptical galaxies, which you see on the right. And there are different ways that these galaxies can form. If two galaxies do collide, that's going to change the shape of the galaxies, as you just saw. Generally, that's one way to lead to irregular galaxy shapes, is when you have the force of gravity and other things shaping these galaxies as they interact. Eventually, after a galaxy collision, you might lead to an elliptical galaxy shape, but there are other ways that these shapes might develop as well. As I mentioned, we aren't around to watch these processes, but because we can see so many different galaxies out there in the universe, we can figure out and model with computers how this is actually happening. So that's galaxy change. It happens over billions of years, but change happens in the night sky on a shorter and smaller time scale as well. As we've discussed in previous webinars, galaxies are filled with stars and dust and gas, and all of those things are changing as well. So right here, this is actually a picture I pulled earlier today. This is the astronomy picture of the day today, if you guys are familiar with it. The website is up there, APOD. Changes Daily is a nice little resource if you're looking for some beautiful images. And Mary has just added a poll for me up there. If you guys want to take a moment and try answering this question, according to scientists, stars were created when? Well, looks like we've got most of you who've answered, and it looks like everybody has answered many different times, which is correct. Stars are continually being created. I believe on this one, about 60% of students got it right. The big misconception here was that stars were created at the time of the Big Bang. About 20% of the students who took who answered this question had that misconception. There are actually stars being born right this very instant. We may not be able to see them because they're hidden behind dust, and there's also the fact that that light is going to take some time to make it to us, as we talked about before. But those baby stars are out there, and those stars are fusing elements together, like we talked in the first poll. Mostly hydrogen to helium, eventually other things as well. And those stars are eventually going to die, become dust, and that dust will join new stars or planets. And we'll look at that as we go through these next couple images. So I'm going to point out the Pleiades, first of all. This last time, I believe I talked about the universe discovery guides, and in them the cosmic survey activity. In the cosmic survey activity, one of the items in there is the Pleiades star cluster. That's been highlighted in a different universe discovery guide, which you can see here. This is the March one. The Pleiades are only about 100 million years old. What that means is that when the dinosaurs, how I like to bring this up to your average museum visitor, is when the dinosaurs were looking up into the sky, they could not see the Pleiades star cluster. It did not exist. That is something that has been born since the dinosaurs went extinct. So there are lots of different stellar nurseries where stars are being born up there in the night sky. Many of the nebula out there are where dust and gas are forming stars. In this particular picture, called the Mountains of Creation, there are young stars that are creating forces that are acting across light years to push dust and gas away from them. And that kind of forms these pillars that are here. But inside those tips of those peaks, you might be able to see new stars coalescing. And that's what's holding that particular peak together while the area around it is being acted upon by younger stars that have been formed. So there are all sorts of different stars that form, and it depends on how massive they are, how much material has collected. The more massive a star is, the hotter and faster it's going to burn, and they may die out, and the hottest ones may die out in only a few million years. Other ones, like our sun, may last a little bit longer, approximately 10 billion years. We're about halfway through that right now. Tiny ones, like red dwarfs. Many of you may have heard about the TRAPPIST-1 system back in February, those 7 Earth-sized habitable planets all around one star. Those are surrounding a red dwarf, which is a much smaller star. It's actually, the volume of it is only just a little bit larger than the size of Jupiter. Its mass is a little bit more. But something like that is supposed to last for trillions of years, which is really impressive considering that's thousands of times older than the universe since the Big Bang. There are other factors that play into this too. There are some variable stars out there that change in brightness over time. Sometimes that's because the star is getting bigger and smaller as a result of internal forces. We've mentioned those before. You might remember way back, one of our earlier webinars, we talked about Henrietta Leavitt, who discovered the relationship between the rate of fluctuations between what are known as Cepheid variables and their average brightness. That was really key for figuring out the size and the expansion of the universe and measuring how far away many of the things in our universe are. It's with it that we managed to figure out that there are actually things beyond our galaxy. And Dr. Lou Stroller is going to talk a little bit later about other ways we measure distances, but we couldn't have gotten that without Henrietta Leavitt's work. There are other ways that stars may appear to change in the sky besides those Cepheid variables. There are eruptive variables who get brighter in more unpredictable ways. Eta Carinae, which you can see there on the left, has varied between being the second brightest star in the sky and also being invisible to the naked eye over the past 200 years, which is a really big change in what it looks like to us. The star on the right, you can see 4 different pictures of. This is V838 Monocerotis. It went through an event about 15 years ago, and what we were able to see in there was the event happened at the star at first, and then the light from that star went out to these clouds of dust that were already around the star and started to light them up. And we were able to actually, and because it took a little bit longer, few months for the light to get to those clouds of dust, we saw those clouds of dust light up a couple months afterwards as the light finally got to Earth. I say the event happened about 15 years ago. I should clarify, we saw the event about 15 years ago. It actually happened 15 plus however many light years Monocerotis is away. But that star changed dramatically over the course of months and continued over the next few years as well. I've got another visualization here talking about planetary transits. So stars might just appear to change in brightness to us here on Earth if there's something else, like another star or planet tugging on it or orbiting around it. This is actually one of the ways that we can find planets in other galaxies, or not other galaxies, in other solar systems within our galaxy. We can't quite see that far, that well. And I'm going to play this so that you guys can see a little bit about how this works. So what you're seeing here, and I'm looking at the screen right next to me, is a planet passing in front of this star from our view on Earth. And the amount of light, you can see in that graph in the lower left, decreases as the planet is in front of the star. Now, it doesn't drop to 0. It's not like there's a total eclipse of the sun, like many of you may have seen a few months ago. I'll play that again one more time. All that's happening is that there's this just very small decrease, maybe only a % or 2 or even less than that you need a very sensitive instrument to be able to see. And we'll talk more about how this detection works in the next webinar when we get to focus on a little bit more on exoplanets. But it's another way that we might see differences in the night sky. Just as stars are born, they eventually die. They fuse their hydrogen that they're made of into helium, and then eventually that gets used up, and that helium may end up fusing, and depends a lot on the exact type of star what happens. But many of them will form beautiful planetary nebula. You may have seen some of these pictures online. So these are some of the most famous Hubble Space Telescope pictures up here. And there are also a few other pictures up here. The ones that have a little bit more purple in them. These are some multi-wavelength images that contain some observations from Chandra. I think there's a Spitzer picture up here as well somewhere, or some Spitzer information in one of these. Oh yeah, the top right one, I think. In some of them, so this is gas and dust that starts outgassing from them at the end of their lives, and they give off this material that leaves fascinating patterns before the remaining portion of it collapses. And you can see that remnant here. In the middle right, okay, thank you, Patty. That's the cat's eye. I see, Mary is asking which one is the cat's eye. Patty is guessing the middle right. This one. Or this one, that's not the cat's eye there. It's a different one up here. Let other people take a guess as to what they might think that is. Yep, Mary's got it. Middle left, right over here on the far left. And actually, if you look really closely, it says cat's eye there. But you need good eyes to see that. So in some of these images, while you're looking and trying to guess what some of them might be by their name, you can see the remaining core of some of them. There's a white dwarf on many of these. So all of these on the bottom left, it's a little bit easier to see that bright spot at the middle. You can see them in a few others. This is, again, going back to it's easier to see certain things in particular wavelengths of light. Okay, Mary, which one is the Ring Nebula? Before we move on, I'm going to take these pictures away. Yeah, right here. That's the ring. So let's see, that white dwarf is a small, dense remnant where there's no fusion taking place. Eventually, that'll cool down. Eventually, it would become a black dwarf, but our universe isn't old enough for that to have happened yet, as it gives off more energy in the infrared. If the remnant that happens after the outgassing would be over about not quite 1.5 times the mass of our sun, it's 1.4 times the mass of our sun, 1.44, something like that, which is known as the Chandrasekhar limit, a supernova is going to take place instead, which is going to leave behind a neutron star or a stellar black hole, or possibly even nothing at all. There's a few variables that go into that. This is the Crab Nebula here. You can see it on the left in a bunch of different wavelengths. You can see each of the different individual wavelengths, on the bottom. And on the right, I've got the X-ray a little bit bigger, because you can see that little bright dot in the X-ray is the neutron star that's been left behind after the Crab Nebula went supernova. Another fun thing about the Crab Nebula is that this neutron star is a pulsar. What that means is that it's spinning on its axis, just like the Earth rotates on its axis, but it's rotating very, very rapidly, and the beam, and along that axis, it's emitting some really high energy light out, and that beam sweeps over the Earth like a lighthouse. And it does that dozens of times per second, so it looks like it's pulsing there. Hence, and that leads to the name pulsar. And those are some really energetic things that we're able to see here from Earth. Another supernova, and so that was the result of a supernova that happened a while back. I think Crab Nebula was about 1,000 years ago. Is that right? Yep. Thanks, Brandon. In 1987. If anybody was looking up in the skies back, much easier to see in the southern hemisphere. I think a little bit of the northern hemisphere could see it. There was a supernova that went off in the Large Magellanic Cloud. It looked like a new star in the sky, and it was visible to the naked eye. NASA's great observatories like Hubble and Chandra and Spitzer started studying it when they launched in the 90s. And here I've got a series of Hubble observations. So what this looked like with these great telescopes. And you can see how this actually has changed over the course of our lifetimes. And what's happening here is actually the shock wave from the supernovas getting out to this ring of dust that was already out around the supernova, and it's starting to compress it, and it's giving off more and more energy that we're able to see. And I believe this year it started to enter a new phase where I think that ring is starting to dim a little bit. Correct me if I'm wrong, Brandon. So that's another way in which it's changing. You'd actually see the dust in the center of this a little bit too. One of the people here at Space Telescope likes to say it looks like Homer Simpson's head. You can see that. Right there, it's starting to look a little bit more like it. So Homer Simpson is up there staring down at us. But another way that night sky keeps changing. So I mentioned that if the remnant of a star is over about 1.4 times the mass of the sun, that is, it'll go supernova. Well, that number was figured out by Subramanian Chandrasekhar. And that number is basically the maximum mass of a stable white dwarf. If you get more mass than that, you end up going supernova, whether that happens to be while the star is dying or if that happens later. And Chandrasekhar was an astrophysicist originally from British India, which is in the area which is now Pakistan. He did some work at Cambridge, eventually came to the United States out at the University of Chicago. And he actually calculated that limit of when a star would go supernova at the age of 19. And then he continued doing a lot more amazing work in lots of different areas of astrophysics throughout his life. You can see a picture of him there. I think that's another supernova remnant that I've got hanging out there on the right. And I Chandrasekhar, you might notice his name has a little bit of similarity to the Chandra Space Telescope. Well, that's because it was named after him. He was a major person this past century that's contributed to our knowledge of the stars. Another piece about supernovas is that they will give off gamma rays. Remember back to the electromagnetic spectrum we were talking about early on in the series. Gamma rays are the highest energy of light, more energetic than X-rays. And they're another way that the night sky is changing. If you actually had eyes that could see gamma rays, you would see a new event up in the sky every single day. The picture we're looking at here is not actually in gamma rays. Gamma rays don't really form the best images, at least not at this point in time. This is a gamma ray burst that was originally detected in gamma rays by NASA's Compton Gamma Ray Observatory. And this image was taken in visible light by the Keck telescope, which is a ground-based telescope. And we currently have missions like Fermi and Swift that are up in space detecting these sorts of events now. What happens is that those gamma rays end up, the energy from the gamma ray burst heats up other things like gas and dust, which then emit other light, and we're able to detect that for longer periods of time as an afterglow. But gamma rays are the most energetic things that we're aware of happening up there. And supernovas are one of the many events that might give them off, but they're one of the more familiar ones to the average person. So after that supernova, after the star outgasses and collapses, it's going to, I've got the life cycle of a star here. So as it gets old, it may turn into a red giant or a red supergiant, and then either a planetary nebula or supernova, and then you've got dust left over. And on the bottom, this is actually an infrared picture from Spitzer of the Andromeda Galaxy, and we're able to see everything that's glowing. This is warm dust that's glowing. It's much easier to see the dust in the infrared. And you can see how much dust the galaxy is made up of very easily here. That dust is made up of heavier elements, heavier than hydrogen and helium, that are the result of fusion that's taken place in the stars. And actually, all of the elements heavier than iron have come from a supernova or some other sort of stellar process. And that means if you think of the Earth, well, most of the stuff here is not hydrogen or helium. We've got a lot of carbon, we've got a lot of oxygen, iron, other nitrogen, other elements here. The Earth and all of us are made of this stardust. So we are made of the stuff of stars. And without some stars having died before, we wouldn't be able to be here having this little chat. And right here, we've got a artist's impression of a protoplanetary disk. So that dust that goes out into those massive clouds, those nebula, may start to gather when perturbed by an outside force. Maybe it's another supernova happening from another star, and it starts to push on that, or there are stellar winds, and that's going to form this disk where eventually enough material will collapse and form a star, and other dust circling around it may accrete into rocks, and then eventually planetesimals, little tiny, not quite planets, and then those will collide and eventually lead to planets. And that's how we, in a nutshell, end up with places like our solar system. I love that quote, Mary. Oh, and so does Brandon. All right, so that is what wait, I missed one. I hit the thing twice. Right, gravity waves. You guys may have heard about this little thing called the Nobel Prize that got awarded last week. And that got awarded for the detection of gravity waves from colliding black holes. So that's another way that the universe can change. There are many more things out there. Colliding black holes are kind of interesting because we could not detect that sort of thing until the folks who got this Nobel Prize and many, many others, because this is a huge team that deals with this, created these massive detectors, because black holes don't give off light. We can't detect light from that sort of collision. And now that we've got these gravity wave detectors, we know that this sort of thing happens. We didn't know that before. And we're hopeful that in the future, we'll be able to learn other things from those gravity waves as well. So stay tuned. But now I'm going to pass it over to Dr. Lou Strolger, who's going to talk a little bit about dark energy and make the connection from supernovas to dark energy and the expanding universe and all these other ways that the universe continues changing. So I'm going to stop sharing so that he can go ahead and share his own screen.
And I'm going to remind you, Dr. Stroller, to unmute yourself.
There we go.
Yeah.
There now. Yes. Yes. So yeah, I keep forgetting this. All right. I'm sharing a screen now, I believe, which I'm going to get.
Not yet.
All right. Almost. It's working on it. Hold on. What am I not hitting? Share screen. There it is.
There you go.
Can you see this now?
You can see your desktop, not your slideshow.
All right. Oh, it's a little slow, it seems like. So, okay. That's fine. All right. Thank you, Tim. That was a great introduction, especially to supernovae, which, you know, usually takes me about 5 lectures to introduce supernovae, and you did it in less than 10 minutes, which is really good. Supernovae, as you already know, are you know, the stellar endpoints to a lot of different types of stars. In the late 90s, we found out that they can be very useful, specifically these type 1a supernovae, for doing a very interesting experiment. In this image you see on the upper left-hand corner, what you see is a type 1a supernova, that stellar object in the lower left-hand corner, superimposed on its host galaxy. Can you guys see this? In fact, I don't know that okay.
Yes.
Oh, it's different.
It's not there.
Okay, okay. So it's superimposed on its host galaxy. And what you see is basically one star momentarily becoming as bright or even brighter than the collection of 10 billion stars in that galaxy. These are incredibly luminous explosions, which makes them very, very useful for seeing them at very large distance, which is why it's useful is that these events turn out to be excellent measures of of distance. You can see in this diagram on the right is what we call light curves, or how the light evolves from before it explodes all the way through to its maximum light, and then as it decays over the next 80 days or so. What we've noticed about these light curves is they all look very, very similar. In fact, if you were to do nothing and just assume that you can infer how far away an object is just by how bright it appears, you could measure distance from these events fairly accurately, and actually more precisely than we have with any other object of its luminosity to distances that we could do with any other object of its luminosity. In other words, we were able to use this as a standard candle. And this was a really neat experiment that we wanted to run to find out what the history of expansion of the universe looks like. Before I go on in that story, what we also noticed is that the supernova light curves appear to have this weird correlation. That is, that if you look at the brighter events, they all seem to decay or rise and decay at a slower rate than the ones that are even fainter events. This allowed us a sort of empirical correction that we can correct the light curve shape, or correct the light curve, the luminosity of the event by the light curve shape, and arrive at a correction, if you will, to the intrinsic luminosity scatter, arriving at a much more precise distance indicator than has ever been before. We can now measure distances well below a 7% distance indicator. With even more refinements over the last 2 decades, we've gotten that down to something like 2 or 5%, which is far below any other, well, it's at a statistical limit. We're now looking at systematic issues that go along with that. So what this does is, as I said, allows us to measure distance, but that distance depends on some cosmological parameters. How we perceive distance with redshift, or the expansion of the universe, depends on how much matter there is in the universe, whether that be ordinary or dark, and of course, how much energy there is in the universe, whether that be ordinary or dark, and curvature as well. So we wanted to learn what the constituents of our universe is, and figure out from there what the history of expansion of the universe looks like. The upper right-hand diagram is sort of a trajectory, if you will, from the explosion of the Big Bang to now, to what we may see, billions of years from now, tens to hundreds of billions of years from now. And in a cartoon on the left, it shows the same thing. If you have a matter-filled universe, we expect the universe to slow down in its expansion. And even if there were nothing in the universe, this expansion should sort of coast. The idea is to populate that diagram in this very thin sliver of the past that we have available to us with our best standard candles, these supernovae that you see at the bottom, and figure out what the trajectory of the universe is and what the ultimate fate will be. So we did this experiment in the late 90s and found something kind of interesting. Not kind of interesting, I would say it was phenomenal. Rather than slowing down under its own weight, the universe appears to be speeding up, accelerating in its expansion. At least in the last 5 billion years or so, the universe has been accelerating in its cosmic expansion, apparently being driven apart by a repulsive force, which we call dark energy, for lack of a better term. This, of course, was an extraordinary find and needed some extraordinary confirmation to really believe that we have a new standard cosmology. Where I enter the picture is somewhere in my postdoctoral years. I started working on this project with Adam Rees, who received a Nobel Prize for this work, and we used the Hubble Space Telescope to push even further out to see what that history of acceleration really looks like. There was a prediction, a solid prediction, that the strength of dark energy is peculiarly weak, and that it shouldn't have been as strong as it is, or as it is now, in the past. In other words, even further out in the past, dark matter should have slowed down the expansion of history, causing the universe to slow down into an expansion, and only recently give rise to this acceleration that we see. So we tested this. We probed out even further, and indeed, that's what we happened to notice, that this recent acceleration in the last 5 billion years gave way to a past epoch of deceleration, where the universe was not as dark energy dominated and decelerating. So that's what we have. The motions of the universe on the largest scale that we know is that we have a cosmic tug-of-war, where after the Big Bang, there was an expansion, but it's been slowing down due to all the dark matter content of the universe, and only recently has gotten weak enough to allow dark energy to shine and essentially push the universe apart. Where we are currently is a universe that is largely dominated by dark energy, at the 70% level. Dark matter makes up most of the remaining parts, and only about 5% of the universe only 5% of the universe content are the stuff that we are familiar with, the ordinary oxygen, iron, and carbon, and so on, that are created in the furnaces of stars. So that's the history that's dark energy and supernovae.
Well, thank you, Dr. Stroller. So dark energy is one of these things I find it difficult to understand, but I appreciate that the kind of diagrams and you placing it in context of what we would expect due to all the matter and gravity. And I guess we'll, if folks have questions out there, but first I'm going to ask a question first.
Sure.
Which is, so are we just lucky to be observing some 13 billion years after the Big Bang when this acceleration happens to have started within a few billion? I mean, that seems...
Yes, in some ways we are. If we had lived 5 billion years earlier, we would have said this is a dark energy or dark matter filled universe. If we had lived 5 billion years later, we might have said this is a dark energy filled universe. Where's all the matter? including ourselves to some level. So there is a cosmic coincidence of sorts, but there have been extensive reviews of, what sort of tensions there are in the universe that lead to getting us to where we are. And it's kind of a nice thing. And it seems that on one hand, peculiarly, we happen to be in the right place at the right time. On the other, we may not have any opportunity to exist at any other time. So I don't know. We'll see.
So again, if anyone has any questions, and even if you're like kind of speechless around this concept of dark energy, questions in general about the work Dr. Stroller does or anything like that, that would be okay to ask now too.
Sure.
Well, how about I ask a question then?
Sure.
All right.
All right.
So how does this play out in the end? Are we talking about a universe where there's a big rip? Are things going to get ripped apart? Do we know that much to tell that far in advance?
So excellent question. Where we are now is in a period of trying to, we accept that dark energy is out there. We're trying to understand what it is. And as I described, we've named this simply because of its action, not by what it truly is. We don't really have a clue as to what it really is. We have some really good theories for what it should be, and all of them are clearly wrong. So the question is, how wrong do you really want to be? So what we're doing now is trying to zero in on its nature, the very basics of its nature. We understand it's here. We want to know what its strength is to a great precision now, and what it's doing. Is it evolving with time? Is it getting stronger or weaker with time? That requires a tremendous amount of work, as you can imagine, a lot of supernovae, a lot of other surveys looking at how structure has grown from the cosmic microwave background to what we see in the microwave, to what we see in cell structure now, right? That growth of structure also tells us some constraints on the nature of dark energy and dark matter in our universe. So the hope is that we can zero in on its actual value. At the moment, the precision is not as great as we'd like it to be, but a big rip scenario is not out of consideration. It could indeed lead to a point where dark energy does indeed get stronger and stronger over time, to the point where no other forces. Right now, we're seeing gravity lose out to dark energy. Eventually, that could lead to the electrostatic force losing out to dark energy, the weak nuclear force losing out to dark energy, and maybe even the strong nuclear force losing out to dark energy.
Wow, that's a pleasant thought. Wow.
Yeah.
Well, would you, just to brief up on that, would you say that there are any upcoming NASA missions in the next 10, 15, 20 years that will really help us pin this down?
Yes, indeed. I think there are a number of missions, including the NASA missions, that will help us to pen this down. We are working actively so I guess in terms of time frame, Euclid, which is a joint mission with the European Space Agency, will be a dark energy based survey looking for these same signatures, which will add to the number and add to our precision. WFIRST, which we expect to be launched the mid part of the next decade, will collect supernovae. I don't know what we're going to do. We're going to see them everywhere. They're going to be popping off like popcorn. Between WFIRST and, of course, another project on the ground called the Large Sky Synoptic LSST will also find tens of thousands of supernovae, from which we'll be able to further pin down the nature of dark energy. So those three surveys those three are the ones that we're really, really looking forward to.
We do have a question here in the chat. Can this dark energy be harnessed, or is there current research being done to calculate its potency?
Yeah, so it at the moment can't be. So I mentioned that there's a best contender for what dark energy should be, and that is that it's somehow associated with the minimum energy of a vacuum. We don't in a classical physics sense understand that, a vacuum, we think a vacuum is basically nothingness. It doesn't have anything in it. In a quantum mechanical sense, that actually is quite wrong. There is a minimum energy that comes with the vacuum itself. If you try to do this from first principles in quantum mechanics, you end up with a value that is really, really wrong, like 120, 10 to the 120th, so 120 magnitudes of wrongness is basically what we always say. You couldn't be more wrong. Instead, the universe chose a value that was rather close to zero. Not exactly zero, but rather close to zero. That's a bit of a mystery. It's not clear why it should have chosen such a low value. So as I said, I think it could still be a pinpoint, a single value that is a property of a vacuum, or it could be this new force that we've never encountered before. If it's associated with a vacuum, we may have less of a chance of recovering that energy. But if it's something else, we might. I think we got to first recover dark matter, though. I think let's do things in order.
Great. Well, we will continue to take questions online as they come up, and thank you very much for that presentation.
My pleasure. Thank you.
Great. Well, so now I'm going to talk about how, and hopefully I'm on your full screen now, how to convey some of these ideas about our dynamic universe, a universe that's changing all the time, where stars are being born and living and dying, where things are changing, how to engage visitors with some of these ideas. And so a few of the resources I wanted to call to mind. The first one is an exhibition and set of activities and associated multimedia from our colleagues from the Chandra X-ray Observatory. They put together an exhibition called Here, There, Everywhere. And the physical exhibition itself, I'm not sure if it's still available for borrowing, although you can find the contact at this website. But on the website is everything you need to recreate the exhibit yourself. The highest resolution images and labels and all kinds of instructions for doing ancillary activities and demonstrations that go with the exhibit. And the theme of the exhibit is around the physics, the processes that you might be familiar with here on Earth and their analogs in space. So in this slide, you see erosion. So we're familiar with erosion in these sand pillars on Earth, or and in space, the pillars of creation that Hubble observed, the Eagle Nebula, is going through a similar idea. Tim had the slide earlier that showed how radiation and stellar winds were blowing this cloud of dust into these big nodules. And so this exhibit covers this idea that physics that you can experience in space, things like wind, we think of wind as moving air on Earth, but in space you might have solar wind of particles and radiation that, so wind on Earth would cause a dandelion to spread out, and wind in space would cause a comet's tail. And the picture on the lower left is actually a demonstration to do with audiences around the physics of wind acting on things far away. It's one of these wind generate, I forget what they're called, but anyway, you snap the tube, and a visitor who's 20 feet away will feel will feel the wind. So that resource has a lot of activities to talk about some of these processes of change on Earth and in space. Another resource that covers some of the content from this webinar is an activity called the Kinesthetic life cycle of stars. We've talked a couple of times, I think, before about kinesthetic activities, and this one, a URL to the direct description of how to do the activity is at the bottom of the slide, and you see a picture of people doing it, doing the actual activity, and right now they're in the stage of the main part of a star's life, where the core is fusing those elements Tim talked about and radiating outwards, and the outer layers are being pulled inwards by gravity, and everything's in balance. So that's an activity to talk about stellar life cycles, and you get your visitors to go supernova, and they spread out all over the auditorium, so that's fun too. An associated resource, that same activity is included in this larger set of activities called After School Universe, which has a whole bunch of activities like kinesthetic life cycle of stars. It has some activities around simulating what happens during a supernova. And on the left side, there's also a series of video tutorials for how to do these activities. And so on the left side of the slide, you see one video tutorial showing a demonstration of the sudden loss of pressure. I think a lot of museums do this demo in other contexts, but the sudden loss of pressure when the core of a star runs out of fuel and suddenly the star collapses, and that's with a soda can. You can make a soda can collapse with a sudden loss of pressure when you cool down some boiling water in the can. And then below that is another demonstration where you take a tennis ball and a ping pong ball, the tennis ball represents the core of the star, and the ping pong ball represents the outer layers, and you drop it, and the rebound of the ping pong ball is quite impressive. You need to practice so you don't put anyone's eye out, but it's a quite impressive demonstration. So those are all some activities related to the content of life cycle of stars. Another resource related to this whole idea of the universe changing, and a lot of these cosmology ideas, big questions about how the universe works, is a legacy resource. And it was produced actually here at SAO, the Cosmic Questions exhibition. The exhibition is no longer available, but there's a whole set of museum education resources associated with that exhibit that are still available, and those include an educator's guide. The cover of it is here on the right. There's a docent and interpreter's guide full of tabletop activities around the expanding universe, around light travel time and looking back in time, around how the universe changes over time. There's a interpreter's guide at that website. And there's even a science theater script, a play that was actually written by a Boston area playwright, Melinda Lopez, and it's called Girl Meets Boy, a comedy about the universe. And the script for that play is on that legacy resource as well. In terms of understanding more about this idea of dark energy and how we know the universe is accelerating, as Dr. Stroller just talked about, the James Webb Space Telescope video page has an online video that kind of uses these doodles and cartoon to show how the universe is accelerating. Let's see, what time are we here? Okay, so I'm not gonna take the time to show that video. I'm gonna move right along and talk about next steps. So, Erica, what?
All right. I'm going to mute you, Mary, so I can talk and not get an echo for everybody. Believe it or not, with today, everyone can hear me, right? With today, we've passed 2/3 of our webinar series. We've gone through how the universe works and how we got here. Starting in 2 weeks, we'll be going over whether or not we're alone in the universe, our next big question. But what you're really going to be looking forward to is an announcement I'll be making in just 1 second. Mary goes to the next page. We have our draft application up. So anybody that's wanting to know about getting those mini funds, we've placed that on the portal at the very top of the Universe of Learning educator portal. It might change a little bit, but it's pretty close to where it's going to be. We look forward to your questions about it. Please post them on the portal for us. We also want to hear you talk about what program models you're beginning to formulate in your heads and what resources would help you kind of develop these models a little deeper. So we're going to post that question on the portal either today or tomorrow. All right. As I said, the big announcement is the application timeline. We have this ready for you all. I know you've been anxious to hear about it. We're going to open the applications on November 9th, which is the day following our last webinar. The following week, on November 15th, we'll have an application Q&A, so we'll host an informal Zoom meeting. You can come with any questions you haven't already asked on the portal, more clarifications. We'll be here to answer anything that you might want to know about getting those mini funds. Our application deadline will be December 4th, and we'll make a selection for everybody on December 18th. These dates will also end up on the portal, so no worries if you don't have them written down right now. Oh, is there a question? All right, so like I said, in 2 weeks, we'll be getting on with our next NASA big question, are we alone in the universe? And I think that's it for today. So I want to thank everyone for being here with us and Dr. Stroller for giving us a wonderful presentation on dark energy. We really enjoyed having you, and we look forward to seeing you all on the portal and at the next webinar.
Thank you all. We'll see you soon.
All right.
See you later.
Thanks.
Bye.
Thanks, everyone. Hmm.